Hello everyone, my name is Chandan and today I'm going to talk about Xatu, a richer neural network based prediction for video streaming. This work was done at Purdue University in collaboration with Conviva. Let's start by looking at the internet video delivery ecosystem today. The content publishers serve the video using CDNs which are attached to many ISP core networks around the world. The users stream these videos on their playback devices using various access networks such as Wi-Fi, LAN, or cellular networks. The videos are delivered over heterogeneous networks which can have highly variable and challenging network conditions. The internet video today constitutes more than 70% of internet traffic. The users want to watch videos in high quality with no rebuffering. These factors constitute the quality of experience or QoE of video streaming. Many studies show that a low QoE adversely impacts user engagement and revenue. This is why both industry and academia have put lots of efforts to improve video streaming experience. The conventional approach today to improve video streaming is to use adaptive bitrate streaming. In adaptive bitrate streaming, a video is encoded in multiple qualities which we call bitrates. Further, each encoded video is split into multiple chunks. The clients use adaptive bitrate algorithms to pick bitrates for each chunk based on network conditions and buffer occupancy. The ABR algorithms want to choose the highest bitrate that can be downloaded before the buffer gets drained. This operation is repeated for every chunk in the video. Let's take an example and say currently we have 4 seconds of playtime in the buffer and there are 3 different bitrates. The ABR predicts download time for each bitrate. The ABR needs prediction since the future network conditions are unknown. In this example, downloading the high bitrate will lead to rebuffering and both the low and medium bitrate can be downloaded in time. Thus, the ABR will prioritize quality and choose medium bitrate. This is a high-level understanding of how ABRs use prediction to ensure high QoE in video streaming. Now that we have the background in video streaming and ABR, let's look at the contributions from our paper. First, we expose the limitation of existing prediction approaches using data collected from real users. Next, we propose Xatu, a novel prediction approach based on a customized neural network. Finally, we show Xatu's promise in improving prediction accuracy and overall better video streaming experience. Let's look at how existing approaches work and begin by looking at chunk download time in more detail. There are a couple of factors which impact chunk download time. First, we have TTFP, which is the time to first byte, and it is the time from when a chunk download request is sent to the time when first byte is received. Second, we have receive time, which is the time when the actual video chunk is received. Receive time is equal to the size of chunk divided by network bandwidth. These three factors, TTFP, size, and network bandwidth, impact the chunk download time. However, most prediction approaches neglect TTFP. They assume the chunk download time is only dependent on network throughput. Existing approaches maintain a history of throughput and use it to predict future throughput and get the chunk download time. While maintaining the history, they assume that the throughput is independent of chunk size. The current state-of-the-art prediction approach is CS2P from SIGCOMM 2016. CS2P learns from prior video sessions and considers additional features such as CDN, ISP, etc. CS2P pre-partitions video session data based on these features into clusters and trains an HMM model for each cluster to predict the throughput. Next, we analyze the data which sheds light on how these existing approaches work. Our data is collected from real users and consists of more than 100k video sessions spread over more than 80 ISPs and 1000 cities. We first look at TTFP. The x-axis in this graph shows the percentage of download time due to TTFP and the y-axis shows the percentage of chunks. TTFP contributes more than 40% of download time for over 20% of the chunks. Thus, TTFP is a significant contributor of chunk download time and still it is rarely considered in the prediction approaches. Next, we group the chunks based on the chunk sizes and use a box plot to show the distribution of throughput. we clearly see that the application throughput depends on chunk sizes, and the throughput tends to be higher for larger chunk sizes. These can be attributed to TCP effects. Next, we look at whether clustering helps in improving the prediction accuracy. We know that CS2P has a HMM model for each cluster. For comparison, we use global CS2P, which has a single HMM model for all the video sessions in the dataset. In our analysis, we see that for about 35% of clusters, CS2P shows similar or worse prediction error than global CS2P. Thus, using features such as ISP CDN to partition the data is not always helpful and can even hurt the performance. Well, this is because a priori clustering reduces the dataset of video sessions to learn from. It also assumes that the video sessions in the partition have similar network performance, which might not always be true. Now, let's see how our system Xatu addresses these limitations. We know that the video client takes bitrates for chunks using ABR algorithms. These chunks will have different sizes and download times and TTFP depending on the chosen bitrate and network conditions. Thus, we have multiple features for each chunk as a time series and which will be different for each chunk. We call these features temporal features. Xatu model sequences with multiple chunk dependent features and not just throughput. Next, let's consider many time series of download times. To learn from related sessions, Xatu uses several features such as CDN, ISP, time of day, and geolocation. We refer to these features as static features since they do not vary during the session. However, a key aspect of Xatu is it does not simply assume the same combination of features corresponds to similar sessions. Instead, it jointly learns sequence models and which sessions are similar without pre-partitioning sessions. This is crucial as it allows a session to learn from other sessions even if that combination of static features was not previously encountered. We next discuss Xatu's architecture and its rationale. Xatu uses LSTM layer, a long short-term memory layer, which is a special type of recurrent neural network capable of learning long-term or short-term dependencies. There are two key reasons why we use LSTMs. First, it is a sequence model that can be used to predict the next value or next few values in a time series. Second, it is capable of handling multivariate inputs and finding complex relationship between inputs and outputs automatically. A conventional approach to use and combine the input static features and temporal features would be to concatenate them at the input stage and feed to the neural network. However, there is one problem with this approach, that is, the LSTM is not directly aware of which part of information stays the same during the video session, and thus it may take some time to learn the invariant part of the inputs. Also, we wanted to know which sessions we are learning from and would like that control. To address this limitation, Xatu uses a custom neural network architecture that combines the static and temporal features at the output stage using a selective gate. As I mentioned before, the conventional approach is to combine all features in the input stage like the architecture in the left graph. However, Xatu combines them at the output stage. This architecture makes Xatu more interpretable, which means we can see more easily how similar static features can impact the throughput prediction. Let's look at the individual components of Xatu in more detail. Xatu has a temporal features block which takes the temporal features such as size, TTFP, download time, and throughput as input. The temporal block has LSTM unit since it's handling multivariate time series. Next, Xatu has a static feature block for the static features. Xatu does a one-hot encoding for each static feature and passes them through embedding and fully connected layers to output a gate mask for each video session. Xatu uses a selective gate to combine the output of temporal and static features block. Essentially, a selective gate is element-wise multiplication between the gate mask and output of temporal feature blocks. This helps to control the output of the LSTM layer, and we can turn off the output depending on the static features using the gate mask. In this way, we can let the neural network know static features stay the same during the video sessions and also control the LSTM output based on distinct combination of static features. Let's look at the interpretability of Xatu in more detail. We considered the gate mask Z, the output of static block, and use principal component analysis to project Z into a two-dimensional space. In this figure, closer dots indicate that sessions have similar network characteristics. As we can see, many gate masks are bunched together. Thus, it means that learning from these sessions may be beneficial. And this is exactly what Xatu does. It learns from these sessions. Next, we color these dots based on the CDN the sessions belong to. The sessions from same CDN are clearly separated, with top 3 groups in blue from one CDN and the bottom 3 groups in orange from another CDN. Recall, our dataset had 2 CDNs. In the next figure, we separate these dots further based on the time of day. The combinations on the right, red dots, are separated from other clusters. These dots corresponding to 6 pm to 12 am block. Further, the orange and blue dots are relatively close too. These figures exhibit interesting patterns in terms of how these features further separate combinations within the same CDN and time of day. This points to the advantage of Xatu's neural network architecture, which facilitates interpretation of how static features are used. Note, this approach has one more benefit over pre-clustering, since it can learn from models developed with combinations with overlapping features. For instance, in the example, if Xatu encounters a session from a city and ISP for the first time, it could still leverage information from other sessions with the same CDN and time of day. Thus, having seen the design and architecture of Xatu, now let's look at evaluations. To evaluate Xatu, we compared the prediction accuracy with respect to CS2P, state of the art, and then integrate Xatu with ABR algorithms to check the performance of video streaming. For prediction comparison metric, we use the actual throughput of each chunk and the predicted throughput of each chunk, and then use mean normalized absolute error per session as the metric. In this graph, the x-axis shows the error percentage and the y-axis shows the percentage of sessions. We see that the Xatu reduces the median and 90th percentile of mean NAE across sessions by over 23% and 41% respectively. Thus, Xatu does achieve better prediction accuracy. We did consider other metrics to measure the error and found that Xatu consistently outperforms CS2P by over 10 to 25% in median. Next, we integrate Xatu with two ABR algorithms, MPC and Fugu-ABR. In this talk, I'll focus on Fugu-ABR. The other results are shared in more detail in the paper. Fugu-ABR uses a stochastically optimal controller. It uses Fugu-NN, a fully connected neural network, for predicting a probabilistic distribution of download time. It uses only temporal features and does not model TTFP. For a fair comparison, we use a version of Xatu, Xatu Dished, which does not consider static features and TTFP. It gives us a Gaussian distribution of download times using uncertainty quantification. We integrate the two predictors with Fugu-ABR and emulate video sessions and compare performance metrics. For comparison, we use SSIM, a perceptual metric of video quality, and also look at QoE, which is a linear combination of the average video quality, rebuffering ratio, and change of quality during a video session. We observe that Xatu Dished sees a much higher QoE. The difference between Xatu Dished and Fugu-NN is huge for more than 20% of the sessions. Next, we focus on the rebuffering ratio between Xatu Dished and Fugu-NN. We see that Xatu Dished has a median rebuffering close to 0%, while Fugu-NN has a median rebuffering of about 2%. The gap gets bigger for higher percentiles. Xatu shows similar performance improvement when compared with other ABRs such as Pensieve or CS2P integrated with MPC. Xatu improves the median QoE by 29% compared to Pensieve and reduces the rebuffering by over 25% when compared with CS2P and MPC. One goal of the Xatu project is to make an extensible prediction framework such that any new information can be easily incorporated when available. To generalize this observation, we did a controlled experiment to collect the data about which includes information about which serial layer a video chunk is served from. Let's look at an example session where the chunks can be served from either an edge server or a remote server. The throughput from a video chunk served from an edge server is significantly higher compared to a chunk served from a remote server, as expected. When we add this information to Xatu, we see that it improves the prediction accuracy and reduces the median and 90th percentile error by more than 13 and 31% respectively. Thus, Xatu is extensible and can include new features. This concludes my talk, and let's look at the key highlights from our paper. Xatu achieves a 24% reduction in prediction error relative to state-of-the-art CS2P. Xatu's custom architecture helps in interpretability and also reduces the prediction error. Xatu can be easily integrated with multiple ABRs and help in improving video streaming experience. Xatu is extensible and adding new features helps in reducing the prediction error. To top it off, we have released the video session dataset used in our paper. We believe it can be valuable to the research community. Thank you everyone for listening to the talk, and please let me know if you have any questions.